It's a pleasure to introduce Roberto Giménez Conejero from the Mid Sweden University and also Spain. And today he talked about good help pictures of complex maps. Thank you very much, Robert, for accepting this invitation. And you can start when you are ready.
Thank you, Rodrigo. Well, hi guys. It's very nice to see you all again. I want to start by saying that you can stop me at any point. I don't mind having questions in the middle of the talk. I'm going to talk about joint work with Nacho Breva, who is going to be available in archive this week or next week, because we are just finishing some drawings. And I'm going to talk about good real pictures of complex maps. So I'm going to give you some context. I'm going to tell you what is this. I'm going to show you some tools that we use, and then I'm going to explain the results and a bit of how the proof goes. So good real perturbations. So what is this? We are in the context of singularities of mappings. So we consider mappings from Cn to Cp now, n less than p. So we are going to look at the image of this kind of mappings. And we impose some nice conditions like a finite, nice dimensions. These are technical conditions. Okay, in these conditions, we have something called a stable perturbation. For example, for this map from C to C2, it is going to be a plane curve singularity. Sorry, the image is going to be a plane curve. So for this map, x squared x cubed, you have something like this. Of course, the real dimension of this is 2, even though the complex dimension is 1, of course. So this is the image. And the point is that if you take a small perturbation, something may change. And it can happen that you reach something stable, meaning that if you keep deforming this, things are not going to change. So it is stable perturbations. So in this case, a stable perturbation is like this. You add this kind of term here, such that when the parameter is 0, you recover the original thing. And well, the image in the complex case, it changes something like this. You have this kind of transverse double point here, and you have some change in the image, and you have some homology, etc. So the thing is that you have, in the complex case, you have a stable deformation. In the complex case, it is unique. I'm going to repeat this again in a while. And you also have this concept of a stable perturbation in the real case. And the thing is that you have these two concepts in the complex and in the real. And now let's assume that the complexification of the real one is equivalent to the complex one. So you have this. You have the complexification of the real one, and you have this equivalence. We are going to take this equivalence because we want to avoid things like this. We want to avoid like this kind of complex coefficients. Sometimes they are unavoidable, but if we can avoid them, then we do it. So we want to look at the real thing, even by this change of coordinates in source and target. So we consider this, and we're going to say that this real perturbation is a good real perturbation or good real picture if the Bethe numbers of the real image and the Bethe numbers of the complex image, they coincide whenever this is not 0, whenever the complex one are not 0. So if this is not 0, the Bethe numbers are going to be the real and the complex. And we say that it is a complete good real perturbations if they are always the same. If this is 0 or not, they are always the same. For example, in the previous example, we had this stable perturbation for S non-zero. And in the real case, if the parameter is 1, you have this deformation, this perturbation, and inside the corresponding complex picture, it would look something like this. And of course, this has no Bethe number. And in the other case, where the parameter is -1, inside the corresponding, because the fibers are not the same, because they live in different places. But if you look at the fiber and you look how it is inside, it is something like this. And in this case, it's very easy to see that the complex and the real image, they have the same Bethe numbers. So this would be a good real perturbation and also a complete good real perturbation. Okay, so this is the concept that we are going to work with. If there is any question, please stop me. Okay, so the complicated thing about this is that the real deformation, it is not unique. The complex is unique in many senses, but the real is not. So the real, there is not a unique stable perturbation. You can have several. And also it is going to depend on the parameter, because if you take the real line minus the origin, it is not connected. So it is going to depend, the image is going to depend on the sign of the parameter, for example, like before, like we saw here, it depends on the parameter. So, but you also have more deformations, and this is going to matter. So, okay, this first definition, it is the usual definition of good real picture, but we use both in our work, and we use even a third one, and we also deal with M deformations, which I'm going to talk about later. So this is the usual definition, and the first question is, okay, are they equivalent? Because maybe they are not, and we are going to show that they are. And I'm going to explain this in the talk as well. So what is known about good real perturbations? Well, what kind of mapping with the previous conditions, n less than p, so we look at the image, etc. What kind of these mappings have good real perturbations? Well, we have a complete introduction of this in the preprint, but let me give you some references. The first references is from Acampo and independently Gussein Sade, which they were not worried about good real perturbations, but they were worried about something equivalent, which is you have a plane curve singularity, and you wonder if you have a real deformation with a maximal number of double points. So if you can realize the delta invariant of the curve in the real deformation as a real deformation. But in these dimensions, it is equivalent to having a good real perturbation, like in this example. In this example, it happens. And also in this example, you have this and this. They are good real deformations and what they look into. So this is the first reference. Then you have Maran and Mond that prove that from C2 to C3, only the S1 and the family HK, only these have good real perturbations. All the others don't have of monogerms. Then we also have a paper of Cooper, Mond, and Picatic that say that if you have a germ from Cn to Cn plus 1, not Cp, but Cn plus 1, and they are of codimension 1, some technical conditions, so the singularity is very easy, so to say, and the rank of the differential is 1 less than the maximum possible, okay, so n minus 1, so we say that they are corank 1. This is a condition that we use. In this case, all the germs have, or in these conditions, they always have a good real perturbation. You have the same kind of statement, the same kind of results for CP, and it is given by Houston. Something else, Mond proved initially when all this started, that if you have a good real perturbation, so the Betti numbers, you know that they are the same, when the complex is not 0, etc., you go from Cn to Cn plus 1. In this case, the inclusion of the real inside the complex, it is an isomorphism in homology. So in homology, it is an isomorphism. And when you go from Cn to Cn plus 1, this dimension, this Hn, it is the only non-trivial homology for the complex image. So this is basically saying everything about the complex image in a way, in terms of homology. And also you have this conjecture of Cooper and Mond, which asks not only in homology, but are they homotope equivalent? Is the inclusion of a good real perturbation in the complex, is it a homotope equivalence? Finally, among all these references and all the other references, there are no mappings of corank 2, so the rank of the differential is smaller. There are no example of good real picture with corank 2 or less. So the rank of the differential less than n minus 1. And there is a paper of Mond that Amon and I think also Roberta Vicatic, that they show that the simplest case of Corang 2 singularity, it doesn't have good general picture. So even if this condition is this A codimension is 1, in Corang 2 they don't have, at least some examples, they don't have good general picture. And this, so in all the other references, you don't have Corang 2 singularities with good real picture. This conjecture was already a question in another paper, and we solve the conjecture, and even we solve a generalization of the conjecture for other dimensions, because this is only for Cn to Cn plus 1. We solve it for Cn to Cp with an extra thing. Okay. So what do we use to prove this conjecture and all the results that we prove? We use the multiple point spaces. If you want to look at images of mappings, you have to use multiple point spaces. So if you have a mapping, the multiple point, it is very easy. It is just the k multiple points are k tuples of points that have the same image, but the points are different. And then you take the closure of this to include some equalities here. And I'm going to show you an example of this, don't worry. Okay, so you have many points that go to the same image, but they are not the same, basically, and then you take the closure. It is very easy to see that the group of permutations, it acts on this set. It's very easy by just permuting the entries of the k tuple of points. So you have this action, and by means of this action, you define some special homology that I will show you an example in a bit. So basically, you take a chain complex. It is a usual chain, the simplicial chain complex, but you only take those chains where the group acts nicely. This means that the group acts by the sign of the permutation. So if it is a transposition, it simply is it acts by -1, for example. I insist, I will show you an example of this. And then you take the homology of this chain complex. That is the AH. If you take these guys, there is a machinery called image computing spectral sequences that you feed them this kind of special homology, and they give you the homology of the image. So, and I'm going to show you an example now. So, in the previous example, this kind of cusp, the stable deformation of the cusp. So you have this. You have these A, B points that go to the same image. So the double points are going to be this AB and BA. So pairs of points that go to the same image, but they are different. And then you take the closure, but in this case, it is the same. Okay, now you take the alternating chain complex. And in this case, what it is are those chains where the group, sigma 2, it acts by the sign. So in the case of a transposition, the sign is -1, and in the identity, it is identity. So in this chain, if you take the transposition, this goes to minus itself. So it is alternating. And then this is the generator of the alternating chain complex. You don't have any more chains of higher dimensions. And this means that the AH0, it is going to be a set because you compute the homology of this chain complex. And all the homologies above 0, they are trivial. Okay, so now with the image computing spectral sequence, you feed them this alternative homology and it computes the homology of the image. In this case, you have to take the sum of Q and P here. In this case, 0 and 1, because it is P plus 1. So this set, it is going to compute you in some way the homology of the image. So you have this set here. So you see that the homology of this image, it is H1, it is going to be set. This is homotopy equivalent to a 1 sphere. Okay, I'm going to show you another example, but I don't want you to understand all the details about this example. I just want you to follow along and just try to see the flavor of these things. So in this case, the source is two disks, for example, and you have these double points. So, okay, so what you see in the picture. So, okay, you have double points that can come from A with itself, A with B, and B with itself. In this case, A with itself, you don't have any double points. A doesn't intersect itself because A is just an inversion. Sorry, it's an embedding. And B, you have points of A and B with itself. For example, points of B with itself, you have all these lines. This point and this point here are going to be mapped to the same place. So this line, it is going to be mapped to this line here. This is the Winnie umbrella, the cross cap. Okay, and you also have the points of A with B. The points of A with B, it is this kind of loop that you see here. Okay, so with B with itself, in the double point spaces, you have pairs of points that come up to the same image. So you have points here and here. That is going to be a point here, so to say. So you have pairs of points. And because of this, because you have pairs of points and you can take the permutation, the action of the group in this line, it is going to be a reflection over the center. So this center, it is going to be found in the closure. This center is going to be this origin, comma, origin. So it is going to be the point, the same pair. So it is going to be fixed by the permutation. And this is how the action acts in this component. And then you have the components of A and B. And of course, B and A. In this case, maybe you can be tricked because here you see some homology in the pre-image of the double points in A, but take into account that you are taking pairs of points. So this kind of loop you don't see because here in the branch of B, you don't see any crossing. You don't see any loop. So when you take the pairs of points, they are going to look like this. And of course, by the permutation, by the transposition, they are swapped. You look at the alternating chain complex. I'm going to be a bit sloppy. There is even a mistake in this slide, but don't worry. So the 0-dimensional chains that are alternated, they are this point minus this point, because when they are swapped, the sign changes. Similarly with this other point. And the one change is this minus this. Again, it is something similar because when you change, when you take the permutation, they are swapped, so it is minus itself. And with this kind of stuff and some extra details that I did not put here, you see that the homology, the AH, in dimension 1, it is going to be trivial because the boundaries of this, they cover all this. So it is fine, you're not going to see any homology. But for the triple points, now for the triple points, you have this point A, B, and B prime here. They are mapped to the same place. So in the triple points, what are going to be the triple points? It is going to be A, B, B prime, and also A, B prime, B, and also B, A, B prime, etc. So all the permutations. And of course, it's not very difficult to see that the 0 alternative chains, they are going to be like this A, B, B prime minus A, B prime, B, plus, so you have to take this kind of thing. You have to take the sum of the signs of sigma and then sigma A, B, B prime. Just, if you don't understand the details, don't worry, this is very easy. So, there are no extra chains of higher dimension like in the previous case. So A, it's 0, it is going to be the alternative homology, it is going to be set in dimension 0. And again, with the image computing spectral sequence, you see that 0 plus 2, you are going to find a homology in dimension 2 in the image. This set is going to give you this set. And this is this pocket that you could see in the image. Okay, so this is the kind of things that we do in the paper. And the nice thing about these multiple point spaces is that Ton and David, Baran proved that for mappings from Cn to Cp in core rank 1, so this rank of the differential, then these guys in nice conditions, these multiple point spaces that are ICs with a Miller fiber, the multiple points of the stable deformation. So for the mapping, you have an ICs, and when you want to look at the Miller fiber, you have to look at the multiple points of the deformation, of the stable deformation. This is one key thing that we use. And the other key thing is that I proved in a preprint that in the same conditions in Corang 1, instead of looking at the alternative homology, which in general could be very hard to compute or very hard to access, instead of computing this guy, you compute the usual homology, the homology that we know. For instead of the multiple points, you have to take multiple points, but also the subspace that is fixed by any transposition. So if you by any permutation, sorry. So if you have any permutation, it acts on the multiple point space. You have a set of fixed points. If you consider all these spaces, then it is enough to have the same information than with the alternative homology. Okay, so we use these two things. We also use Smith theory, and this is very easy to understand in case you don't know. So if you have a good topological space, and you have also a good action of a P group. So you have a group with P to the alpha elements that acts in a good way in your topological space. In this case, you start by some dimension m, and now you are going to take the sum of all the Betti numbers starting from m to infinity. So you take the Betti numbers modulo P, so you take with coefficients in FP, you take this rank of your space, all these Betti numbers of the original space. This sum is bigger or equal than the same sum, but with the fixed points by the group. And this is easier to see with an example. For example, you have these torus, and now you have the action of the group of sigma 2 or Z2 by this reflection. So the fixed points of these reflections are these two S1s that you see here. And Smith theory, this theorem of Floyd, it tells you that, okay, if you take, starting from 0, for example, you take the sum of all the Betti numbers, this sum is bigger than this sum or equal. In this case, they are equal. If you start from dimension 1 and you go higher, this sum, which is 3, it is bigger or equal than 2. And the same with all the degrees. So you start from somewhere and then you add all the Betti numbers. Modulo in coefficients with FP. Okay, we also use this. And of course, because we have to also work with this alternative homology, we need the version of this theorem, but for alternative homology. So this kind of homology from the alternating chain complex. So you have the same thing, but with alternative homology. And you also take the action of the group. So we also use this. Okay, and what is the idea that we're going to follow? The idea we took it from good real pictures of hypersurfaces. What is this? So if you have a hypersurface or an ICs of positive dimension, this condition is important because in 0 dimension things changes. Okay, so you take the Miller fiber of your hypersurface or your ICs, and you assume that the equations, or I'm going to talk about hypersurfaces, but for ICs it is the same. You took the equation of the hypersurface and you assume that it is a real equation. So this is the Miller fiber. If this epsilon, you take it real and you look at the real solutions of this equation, now you have the real Miller fiber. And of course, the real Miller fiber, it is going to be the fixed points by the conjugation. So you're going to take the real points in the complex Miller fiber. This is, as I was saying, the fixed points by the action of the group. And now, in these conditions, you can apply Smith theory because the action is very nice and everything. So what does Smith theory tells you? So it tells you that you start from dimension 0, you take the sum of all the Betti numbers in mod 2 in this case. So you have the 0 Betti number, and the middle Betty number, which is the Miller number, as you know. This is bigger or equal than the rank of the homologies of the real Miller fiber, because it is the fixed point, but mod 2. This is just Smith theory, usual Smith theory. Now, if you, instead of taking the sum of all the Betty numbers, you take only the 0 and the nth, you have this. This is bigger or equal. This is, less or equal than the previous one. So taking some terms. And now, if you use Poincaré duality, or, Poincaré duality. So part of this H0, you are going to be able to see it in the relative homology relative to the boundary. And this, by Poincaré duality, it is isomorphic to the middle homology, to Hn in the real case. So you're going to have 2 times the rank of Hn. So the nth Betty number. Okay. In this case, if you know that the nth Betty number of the real and of the complex, they are equal, this change of inequality gives you this inequality. So 1 plus the Miller number is bigger or equal than 2 times the Miller number, because this guy, if they are equal, they have to be the Miller number. So all this, I insist, only happens in positive dimension, because in positive dimension you have this 1 and this Miller number. Otherwise, things don't work with Poincaré duality, for example. Okay, this inequality tells you that if you have a good real perturbation, mu, the Miller number, has to be either 0 or 1. So either you didn't have a singularity, or you have an A1 singularity, which is the only one that has Miller number 1. So the singularity is very simple. What do we do? Well, this kind of result, it is what we prove. So we prove that for mappings from Cn to Cp, n less than p, the same conditions, say finite, Corank 1, then if f admits a good real picture, we prove that the Miller number of the multiple point spaces, which are ICs, isolated complete intersection singularity, these Miller numbers, they are 0 or 1. So they are either smooth or an A1 singularity, if the dimension is positive. So this is one of our main theorems. And I insist, we use all this machinery of the previous tools that I showed you, and something else that I'm going to explain later. So this theorem, this necessary condition to have a good real picture that the Miller number is 0 or 1, we can use it, for example, from C3 to C4. So from C3 to C4 in Corank 1, we have this classification of Houston and Kirk. And you have these are the conditions on K, on the subindex that you see on the table. These are the Miller number of the double points. These are the Miller number of the triple points. And this is the codimension. In these dimensions, the double and the triple points, they have positive dimension. So the double points have dimension 2 and the triple have dimension 3. So from this table, we know that if we are looking for good real pictures, all these cases we can exclude because they don't have Miller number equal to 1, except A1, when the Miller number of double points is 1, P1, where the triple points, they have Miller number 1, and Q2. Q2, this is going to be 1 and also 1. So these 3 cases, they may have a good real picture. So actually, we already know that A1 and P1, they have a good real picture. Why? Because they are Corank 1, and the codimension is also 1. And by the result of Cooper-Mond and Picatic, we know that these guys, they always have good real picture. So this we know. About Q2, this is something new because the codimension is 2. The codimension is 2. In this case, our tools, they also work to show that this case also has a good real perturbation. So this case also has. And actually, because we were inspired by this example, and we think that probably our techniques give the converse as well, meaning that if you have this condition that the minimum number is 0 or 1 when the dimension of the multiple point space is positive, if you have this, then you have good real picture, like in the case of Q2. The problem, the technical problem that we are facing is that, okay, if this has positive dimension, then we more or less know what to do and everything, but what happens when this has dimension 0? Well, when this has dimension 0, they are still ICs, but it is not so easy to see because maybe you have bigger Miller number and many things could change. And about this, I wanted to comment something because I haven't put in the slides, but there is the concept of M deformations. An M deformation is a deformation. A real a complex thing has an M deformation. If you have a real deformation, where you find all the zero-dimensional things, all the zero-dimensional information. M deformations, they are known to exist in many cases. There are results by Cedinha and other co-authors, for example. Well, we think that this complication, this problem of ICs of dimension 0, it is very related to these M deformations. But this is just future work. And by the way, we also proved that any good real picture is an M deformation in current one. Okay, let's continue. And I insist if you have questions, you can stop. I'm going to talk about the proof of this, about the idea of the proof, because there is another concept that I didn't introduce. And it is the whiskers. So now you take something that locally it is stable. If you look at each point, at the germ at each point, it is stable. You don't have any problem. You deform this and you get the same thing. So you have a mapping that is locally stable. And also it is a complex map. Assume that it is the complexification of a real thing. Okay, like we were doing before. The whiskers are the following. So you take the complex image, and now you take the intersection with the reals. The thing is that maybe this is not exactly the real image, the image of the reals, of the real of GR. But if you take exactly this, if you take away the real image, and now you take the closure, these are the whiskers. And I'm going to show you an example. For example, for this very easy case, for the crosscut, the wing umbrella, this is R2. The image of the crosscut is like this. This is the real image. But if you take the complex thing and then you take the intersection with the reals, there are some complex points that go to real image. And it is exactly these whiskers. If you want to see this in another way, it is you have this kind of set in R3 in this case, or in RP. If you take the Zariski closure, the whiskers is what you have to add to have the Zariski closure. So either you see that they are what you are missing from the Zariski closure, or it is the image of the complex points that go to the reals. So the complex image intersected the reals minus the real image. In this case, it is this. And this object is very tricky because it gives you a lot of problems. Because, well, I'm going to show you now. First of all, we prove many things about these whiskers. Some things were already known by Mon, for example. One very easy thing to see is that the dimension of the whiskers is less than the dimension of the real image. For example, in this case, this has dimension 1 and this has dimension 2. These kind of things always happen. The whiskers are preserved by change of coordinates. This is not hard to see because we are working by this A equivalence. We need this. This is very important. The whiskers are only empty when you have normal crossings of embeddings. So when you have double points, etc. In this case, you have whiskers because this singularity, it is not a normal crossing of embeddings. So that is why you see whiskers. And this happens all the time that you don't have a normal crossing embeddings, you have something. And this is a bit more technical. Okay, so now we are taking the multiple point spaces, the multiple points that go to the whiskers. This is this WK. So these points that go to the whiskers in the image, so the multiple points that only that give you the whiskers, these guys, when you take the intersection with the real multiple points, with the actually real multiple points, this intersection, it is in some fixed, in some space fixed by some permutation. So this intersection, it is going to be fixed by some permutation that is not the identity. And this is absolutely key to everything that we do. With this kind of idea, we are able to split the real multiple points, these guys, with the multiple points of the whiskers, because you find them in some fixed points by some permutation. Because of this fact, we can prove the following. So now, this is going to denote the restriction to the whiskers, and this is going to denote the restriction to the reals. So you have, this is the real image and the whiskers. This is everything. These image computing spectral sequences, this is the E1PQ. These multiple point, the image computing spectral sequences, they split because you have this mapping, you have this mapping, and you have this mapping. You have everything, you have only the reals, and you have the whiskers. All these are mappings. Each one of them have an image computing spectral sequence. So what happens is that the sequence, the spectral sequence of everything splits into the sequence of the reals and direct sum the sequence of the whiskers. This is not absolutely accurate because there is a small thing that we have to add to the theorem, but it is basically true. And because of this, we are able to split the reals and the whiskers in a nice way by this image computing spectral sequence. And what this allows us is, so remember, good real perturbation when the Betty numbers are equal, whenever this is not zero, and complete good real perturbations when they are always equal. This kind of theorem of the image computing spectral sequence allows us to prove that they are equivalent without the condition of column one. This is always true. So good real perturbations are always complete good real perturbations and vice versa, which is trivial. In particular, the Euler characteristics of the real image and of the complex image, they are equal. And this is also something that we use in the paper. How do you prove this? Well, this is Smith theory. So you have the image of the complex points, modulo 2. And you have the Betty numbers of these guys, modulo 2. By Smith theory, you know that there is an action of by conjugation, and the fixed points of the conjugation is the real points in the image. So you have the image of the complex intersected the reals. This is not the same as the image of the real map, because you also have the whiskers. The whiskers are also in the intersection with the reals. So you have this thing, modulo 2 all the time. Now, this guy, which contains the whiskers, it is here. By the previous result, I told you, okay, this splits into the reals and also the whiskers. So if you take only the reals, you have this inequality here. So this step is taking only the reals by the previous theorem. And now, if F is a good real perturbation, you have this. Okay, whenever this guy is not zero, this and this are equal. And whenever this is zero, I don't know if this is zero or not. So we have the inequality. So in case it is a good real perturbation, you have this. Now, if all this happens, notice that you started with something and you end up with the same thing. If this happens, everything has to be an equality. if everything is an equality, whenever this is 0, this also has to be 0. And this is exactly the difference between a good real perturbation and a complete good real perturbation. So when this is 0, this has to be 0. And good real perturbation only meant that whenever this is not 0, this is equal. Of course, there is the detail of that we are working with modulo 2. But there is a very easy trick, which is, okay, you're taking modulo 2 coefficients, blah, blah, but the image, the complex image, it is homotopy equivalent to a wedge of spheres. This means that the homology is free. You don't have torsion. This means that these Betti numbers, they are equal in modulo 2 or with set coefficients. So nothing changed. This is the sum of the Betti numbers. Now, you have this inequality with F2. Of course, if you change from F2 to Z, maybe you have even less things on this on this side of the equation, because every free thing gives you something modulo 2, but also if you have something modulo 2, it also gives you something modulo 2, of course. So you still have this chain of inequalities when you change from the free to the modulo 2, and you have the proof is the same, basically. Okay, so finally, I want to address this conjecture by Cooper and Mond that now we know that the homology, at least the free part, the Betti numbers, if you have a good real perturbation, they are the same, because you have a complete good real perturbation. In any case, not Corang 2, not Corang 1, in every case. Now the question is, okay, this is something in terms of homology. Do you have the same thing in homotopy? And the question is this: if you have a good real picture, is the inclusion of the real in the complex a homotopy equivalence? Well, the conjecture, it was stated from Cn to Cn plus 1. This conjecture we prove. If you want to generalize this conjecture from Cn to Cp, you need to add the condition that it has Corang 1 in our paper. In these cases, we also prove the conjecture, but the original conjecture it is solved. Okay, how do you go about proving this conjecture? Well, first, you know that the ranks of the homology, they are the same, but you don't know that the inclusion gives you an isomorphism in homology. So if you're able to prove that the inclusion gives you an isomorphism in homology, not only that the homologies are isomorphic, but that the inclusion gives you this isomorphism. If you're able to prove this, by Whitehead theorem, if you can prove that the real image is simply connected, then this is going to be a homotopy equivalence. So what do? You have to prove this. This is the non-trivial part. This is the easy part. So proving that the inclusion is an isomorphism in homology, the proof changes depending if you have a map from Cn to Cn plus 1, then the proof is 1. And if you go from Cn to Cp, you have another proof that only works in Corang 1. That is the reason that we need to add this extra condition. Well, you have this proof for the homology, and then about the simple connectedness, if we use a theorem of Houston, that says the following, that is going to be satisfied in our case. If you have a map, this is just a topological map. This is not complex or anything. If you have a map that is proper, it is finite, and it is a surjective stratified summation, all this happens in our case. Then if X is path connected, which also happens in our case because it is Rm or a ball in Rm, and there is, or the image of a ball or something, and there are points with only one preimage, which also happens in our case, then if the multiple points, if the double points have zero alternative homology, which also happens, I insist, then the induced mapping in homotopy is a surjection. So what do we want? We want that this is trivial. So what we're going to do is just do all this for the real map. In the real map, all these conditions are going to be satisfied or the proof is trivial or these conditions are satisfied. And what you're going to have is that the fundamental group of Rn, which is trivial, surjects into the fundamental group of the real image. Then it has to be 0. And this is, it has to be trivial. This is exactly what we want. So this concludes the proof of the conjecture. Modulo proving this part, which is the non-trivial part. And with this, I have finished. Thank you very much for your attention.